Hi everyone, it's Wednesday, so that means it's time for another live stream from Chem Help ASAP. So I hope that you are having a good Wednesday. So this week, as you can see, we are going to be doing propagation of error. Now, this is a topic that's maybe a little more associated with analytical chemistry than general chemistry, but I think it's kind of interesting and cool, so I wanted to share it with you. Okay, so let's get started. All right, so the first thing that I want to talk about is just the different types of error that you encounter. So we split error up into really two main categories. We have systematic and random error. So systematic error, this is going to come from either a problem with the equipment or some kind of flaw in the design of the experiment. So I had an example here, a poorly made ruler. So say you had a ruler and you were measuring things for a lab, but the ruler was off by like half a centimeter. Well, that would be systematic error. You have a tool that is not functioning the way it is supposed to be functioning. Or if you're using a tool that you're not familiar with, say you're using calipers and you're consistently using it wrong, that would also be a systematic error. So when you find a systematic error, it's usually pretty easy to eliminate. So if you've got a ruler that is not actually measuring accurately, then you would get rid of that ruler and get one that does measure accurately. Or if you were unfamiliar with, say, how to use calipers or a piece of equipment, then you would get trained on how to use that properly. So that would get rid of systematic error. Okay, the other error that we encounter is random error. Now, this is very difficult to control, and you can't control all of it. Obviously, you try to minimize any kind of error as much as possible. So, when you have, say, different students reading a ruler, so you have a ruler maybe that is accurate, but everyone's going to read a measurement between the tick marks just a little bit differently. That is random error, and you cannot entirely get rid of that error. So what we are going to be focusing on in terms of when we propagate errors, we're really going to be focusing on random error, because again, the systematic error, hopefully you are getting rid of as you either do the experiment and realize there is systematic error, or as you design an experiment to minimize that systematic error. Okay, so that is our types of error. Now let's talk about the actual propagation. So this is where we talk about the different kinds of what we actually call uncertainty, although you'll hear uncertainty and error used interchangeably, and that's totally fine. Like we talk about this as propagation of error, but I'm getting ready to talk about uncertainty, especially in the scope of just this live stream and this kind of low level analysis of error. It's fine to interchange error and uncertainty. Okay. With that being said, an absolute uncertainty or an absolute error, this is the error that is associated with a particular measurement. So the example here is a 20 milliliter volumetric pipette. So a volumetric pipette, of course, is designed to deliver a certain volume of liquid. So if you had one that was supposed to deliver 20 milliliters, then you would probably see, like on the neck of the pipette is usually where you find it, that its volume is 20.00 milliliters, and then you would have this plus or minus 0.02 milliliters. Now, again, this is, some are more accurate, some are less accurate. That means when you deliver this 20 milliliters, you could be delivering as little as 19.98 or as much as 20.02. So it's plus or minus that 0.02 milliliters. This is a random error. It is inherent in the volumetric pipette. So it is an error that is part of the equipment. A systematic error would be, say, you're continuously using the volumetric pipette wrong. Okay, that would be something you try to eliminate. Okay, That is absolute uncertainty, but we also want to be able to calculate relative uncertainty. Now, when you do a relative uncertainty, what we're going to do is we're going to compare the error in the measurement to the magnitude of the measurement. And we actually do this mathematically when I say compare. So we calculate relative uncertainty by taking the absolute uncertainty and we're going to divide it by the magnitude of the measurement. So if we go back to this volumetric pipette, the magnitude of the measurement is the 20 milliliters. And of course, the absolute uncertainty is the error associated with that. So if we were to calculate the relative uncertainty of this volumetric pipette, we would simply take 0.02 divided by 20 milliliters, and that would give us a relative uncertainty of 0.001. Now, we actually don't usually stop at relative uncertainty. We need to calculate percent relative uncertainty. And as we do our problems, this will become a little more evident. So the percent relative uncertainty, of course, you just take your relative uncertainty. You can see the calculation right here, and you're going to multiply by 100%. So continuing with our volumetric pipette example, we would just take our relative uncertainty, which we've calculated, and you can see down here, multiply by 100%, and this would give us our percent relative uncertainty. And we're going to need to be able to work with both the absolute uncertainty, which is usually what is given when you have a measurement, but we're also going to need to be able to calculate percent relative uncertainty and also take percent relative uncertainty and go all the way back to absolute uncertainty. So again, these are kind of the two main types of uncertainty that we are going to use as we do our calculations to propagate our error. Okay, so I hope that makes sense. And let's actually start with our calculations. Let's make sure there are no questions first. All right. So, oh no, sorry, I forgot I was going to put these equations in first. Then I promise we will get to our calculations. Okay, so there are two different equations we use. We use one type of equation for propagating error when we're doing addition or subtraction, and we use another equation when we are propagating error when we're doing multiplication and division. Now, I know these equations look kind of wild and maybe don't make a lot of sense. They will make much more sense as we actually apply them. But if you're doing addition subtraction, the way you calculate your error for that is you are going to take the sum of all the absolute uncertainties squared. So you're going to take each absolute uncertainty associated with whatever measurements you're adding or subtracting. You're going to square them. You're going to sum them, and then you're going to take the square root. Again, this will become a lot more clear when we actually do an example. Now, remember how we talked about percent relative uncertainty? That is when we get into multiplication and division. So for addition subtraction, we're just using the absolute uncertainty, but for multiplication division, we're using the percent relative uncertainty. So what we usually do is we're often given the absolute uncertainty, and we then calculate the percent relative uncertainty. We then use that to propagate our error, and then we usually come back out into absolute uncertainty. Again, this will make more sense when we actually do a problem. But it just like the error for addition subtraction, you're going to square your percent relative uncertainties, you're going to sum all of those uncertainties, and then you are going to take the square root of that. Okay, now we are going to get to our actual problems. Okay, so we're going to start with addition and subtraction because it's just easier. So here is our addition subtraction. I mean, I've actually already added it there because that's pretty easy to do. And you can see with each of these measurements, and it doesn't matter what they are, they're measured either in grams, or maybe they're measured in centimeters, or maybe they're measured in milliliters. It doesn't matter. I just want to propagate the error here. So I did go ahead and put our equation for propagating our error for addition subtraction. And I'm going to get to this real rule of sig figs after we get through all of this calculation, because we have to get through it first before that makes sense. So now, finally, 10 minutes in, we're actually going to start some math here. Okay, so addition, subtraction. The great thing is we're going to be using our absolute uncertainties, which are given to us here. So these are, and usually you will see them in parentheses, and it's a plus or minus some kind of number, and it's usually a decimal. It doesn't have to be. It depends on what the measurement is. So when I have this 5.92, the plus or minus 0.01 is the absolute uncertainty associated with the 5.92. So to calculate my error for this calculation, because I'm looking for this error right here, like I can do this addition, but I'm looking for the error, this is how I'm going to do it. Okay, so my error for my calculation is going to be a big, long square root. So I need my absolute uncertainty for each of my measurements. Now in this case, I just have 2. That's totally fine. So here is my absolute uncertainty again for my 5.92. I'm going to square it, and I'm going to add to that my absolute uncertainty for my second measurement. So that's 0.002, again squared. Going to make sure this whole thing is under the radical. So let's first just simplify under the radical, and then we'll take the square root. Okay, so if I square each of my errors and then add them together, again, you want to make sure you remember your order of operations too. You want to square them first and then add them together. We get 1.04 times 10 to the negative 4th. Then we simply take the square root, and the error associated with this calculation is 0.010. Now, I want to pause just a second here and explain why I have written this way. So when you report errors or uncertainties, you only report one sig fig in that number. Now, often we will go ahead and report a second one, but the key thing to remember is that second digit that you report is actually not the first uncertain digit. So that is why for this second one, you can see I subscripted that 0. So that 0 is the third decimal place, but by subscripting, what I'm doing is I'm telling the reader of this document, hey, I just wanted to give you an extra digit, but it's really the 1 that is our first uncertain digit here in this answer, but I wanted to give you a second one. And you see this most often, although I tend to do it for all of my errors, but you see this most often when your error is a 1 somewhere. Then you will very often be given the second digit, but again, it's subscripted to say, hey, this is actually our second digit in our error. Okay. With that being said, let's actually write out our answer properly. So now we have our error. So our answer for this problem is 9.894 plus or minus 0.01. Again, I do that subscripted 0. Okay, at this point, I want to bring up the real rule for sig figs because I have just added my 5.92 plus my 3.974, and I just put down what my calculator gave me, and then I propagated my error. But where do I round my 9.894 to? Well, you can use your rules for sig figs, but because you have error, you are actually going to use your real rule for sig figs. And what that states is the last significant digit in your answer, so wherever I round to in my actual answer, is going to be the first digit in the absolute uncertainty. Well, this is my absolute uncertainty, and you can see the first digit in my absolute uncertainty is in the hundredths place, so I need to round to the hundredths place. So my answer then is 9.89 plus or minus 0.01. And again, I'll keep that 0 there, but it's subscripted to say that it is not significant. Another thing you can do, because subscripting can be handy if you just want to show another digit, is you could put the 4 there and put it subscripted, because again, that communicates to the reader, I just wanted to show you this next digit, but it is not a significant digit. So this is actually our real rule for sig figs, is we should actually be looking at the absolute uncertainty associated with whatever number we have, whatever calculation we've done, or however we have actually measured it. Now, our general rules for sig figs are a great place to start, and usually you will find that where you round based on your error is often where you would round based just on your rules for sig figs. So if I look at this problem initially, you can see if I'm just using my rules for addition and subtraction for sig figs, I would look for the number with the fewest decimal places. Well, that would be the 5.92. That's two decimal places, which would give my answer 2 decimal places. And that's actually exactly where we ended up with our error as well. So this is why usually you learn just your plain old rules for sig figs first, and then you come along later. Again, usually it's either maybe a second semester of Gen Chem or an analytical chemistry that you will come along and you will learn how to propagate error and get to the real rule of sig figs. But your general set actually works pretty well too. Okay, let's make sure there are no questions about this one. Nope, everything looks good. So this is propagation of error for addition subtraction, and let's do propagation of error for multiplication and division. This is where I find using parentheses is very helpful. Okay, so I am multiplying two numbers here. Again, this using the parentheses here can help identify, hey, this is actually an error. I don't want you to add or subtract this number to 5.89. This is an error. And so you see that very often. Again, this plus or minus symbol is also a really big red flag to say, hey, this is an error. But I know that sometimes when you're reading through these quickly, at least I have done this, I have read this as just a plus sign. So the parentheses also help me focus in and go, wait. This is an error. Okay, so I'm multiplying my 5.89 times my 0.0358. I've got absolute uncertainties associated with both of those numbers. I went ahead and actually did the multiplication, and now I just want to know what the error is. And I will use my real rule for sig figs and round it at the end. Okay, so our propagation of error equation is here. Again, I know it looks kind of weird. The thing I want you to pick out first from this calculation is we need percent relative uncertainty. Remember that these here are absolute uncertainties. So the first thing I am going to do is I am going to convert each of these absolute uncertainties into percent relative uncertainties. Okay, so let's get back to my pen and let's do this calculation. All right. If you remember, actually, I can pop back here because I couldn't put all the equations in. Oops, not this one. This one. All right, so to get to percent relative uncertainty, we're going to calculate the relative uncertainty, where we take the absolute uncertainty that's given to us, and we're going to divide by the magnitude of the measurement. And then once we have that, we're going to multiply by 100%. So just so you know where these calculations are coming from, they are coming from these equations right here. Okay, now back to our multiplication division. So again, I'm going to do this first error here, this 0.03. So what I do is for relative uncertainty, and I'm just going to kind of abbreviate it there. I'm going to take my 0.03 divided by the magnitude of the measurement itself. And this gives me just my relative uncertainty. Okay, so this equals, and this is where it is easy to drop a zero, and sometimes you might want to go to scientific notation too. Either way, just wherever you're most comfortable. Now you can see with this, I did include the second digit, but I subscripted it because it is not a significant digit. I just wanted to show what it is. Okay, so this is my relative uncertainty for my 5.89, but again, I need my percent relative uncertainty. So to get my percent, I'm just going to call this RU so I don't have to keep rewriting a lot of long words. So this is easy. I'm just going to multiply by 100%, which is just going to move the decimal, but I'm still going to keep my 1, my subscripted 1, just because I prefer to, but of course you don't have to. Now, the key here is make sure you put that percentage mark at the end, because again, that tells the reader, hey, we're not talking about an absolute uncertainty. We're talking about a percent relative uncertainty. And that's a really important distinction to make, especially to your reader, and to know how to propagate error as well. Okay, so that's my percent relative uncertainty for my first term, but I also need to do it for my second one. Okay, so just my relative uncertainty for my second number. Again, I'm going to take the error I'm given, and that's 1, 2, 3 zeros. Again, it's easy to add or drop a 0 in when you're dealing with these small relative uncertainty or absolute uncertainties. Okay, so I have done this calculation, and this gives me 0.011, again with my subscript there. And I need to convert that now to a percent. Oh, sorry, this was just relative uncertainty. I think I said percent. That is not right. I'm getting ready to calculate percent. So times 100%, and that gives me a 1 point, again, subscripted 1% relative uncertainty. Okay, so now that I have calculated my percent relative uncertainties, I can actually use my error calculation here. Okay, so my percent error for doing this calculation, I'm going to have a very long radical. Okay, so I'm going to take each of my percent relative uncertainties, so that is my 0.51%, and it's going to be squared, and I'm going to add it to my second one, which is actually down here. That is 1.1%. I'm going to square it, and of course, all of this is under the radical here. Okay, so my percent error, if I simplify under the radical, I think I have that number, yes, 1.47, which gives me a percent error, or as you could say, again, a percent relative uncertainty. I am interchanging these, 1.2%. All right, now you can report this as a plus or minus 1.2%, but usually it's better to report the absolute uncertainty, because remember, the absolute uncertainty is also how you know where to round when you're using your real rules for sig figs. So your percent relative uncertainty is not going to give you the correct decimal place to round to. You need your absolute uncertainty. So I'm going to erase this. And what we need to do is we need to take this percent relative uncertainty and turn it back into an absolute uncertainty. Okay, so this is where, again, it might be helpful. Let me just pop back to our equations. So we've got a percent relative uncertainty. We will then calculate a relative uncertainty. And then once we have our relative uncertainty, we can get back to our absolute uncertainty. So we're just moving backwards now. All right, so here is our percent relative uncertainty. And what we first want to do is, instead of multiplying by 100, we are going to divide by 100. All right, so I'm going to take my 1.1. Oh. Sorry. I need to subscript. And I'm going to divide by 100%, and that will take me back to my relative uncertainty, 0.0011. Okay, so again, this is my relative uncertainty. And then to get back to my absolute, I'm going to take my relative uncertainty. Remember, this is the absolute uncertainty over the magnitude of the measurement. So I just kind of abbreviated that a little bit there. So this is where my 0.0011 goes. I'm going to calculate, maybe I'll call this just absolute, over the magnitude, and the magnitude of my measurement is my answer up here. So this is over 0.22676 0.5. So now I can calculate my absolute uncertainty, and I have done that calculation, and my absolute uncertainty, or my absolute error, is 0.0027. Okay, so if I am reporting my final answer, first of all, I'm going to use my real rule of sig figs. So my first digit in my uncertainty is in the thousandths place. It's at 2. So I'm going to make sure I round my error to the 6 right there. So my answer is going to be 0.227 plus or minus 0.0027. And again, if I really wanted to, I could report this as 267 and just make sure the 7 is subscripted. That's totally, actually it would round up to an 8 because you've got a 6 there. It really depends on what you like to do, or your professor might have something specific that they want you to do as well. Okay, so that is propagation for multiplication division. You can see that multiplication division takes a lot more work and a lot more calculation. They're not difficult calculations, but it is important that you keep kind of track of where you are. Are you talking about an absolute uncertainty? Are you talking about a relative uncertainty? Are you talking about a percent relative uncertainty? Because all of those are actually different things and put you at different points in your propagation. Okay, all right. So that's great. No questions. The other thing I wanted to do, and this is going to take a little bit of time, is to do a mixed operation propagation of error. So what I've done here is we've got what I consider two terms, maybe term A, term B. We've got a division here, and then we're going to add the two terms together. So I'm going to treat this first as just two division problems, and I'm going to propagate my error. And then once I have answers for that with the error that is propagated, then I will add it together. I will propagate that error, and we will get a final error. So it's going to take a little bit of work. Again, the multiplication division, because we've got to go to that percent relative uncertainty. Okay, so let's jump into this calculation. And I think what I'll do to make this a little bit easier. So yes, I'm going to call this term A and term B, and I'm also going to call this error 1, error 2, error 3, and error 4, just so I can keep track in my mind of where I am and what kind of error I'm dealing with. All right, so we're starting with term A here, and I'm going to do error 1 and error 2. So because I'm doing division, the first thing I'm going to do is I'm going to turn error 1 and error 2 into percent relative uncertainties, because these are absolute uncertainties right now. So I'm going to take I'll call this percent error 1. I'm going to take my 0.03, divide it by, again, the magnitude of the measurement. And just to save a little space, again, this will give me my relative uncertainty, but I want my percent relative uncertainty. So I am going to go ahead and just say times 100%, and that will give me my percent relative uncertainty. You can always break this up into two calculations if you want, or you can do it as one. A lot of times I tend to break it up more in my calculator, but I just keep going with my calculator until I get the answer I want. Okay, so my percent relative uncertainty for my first error is 0.92, again subscripted, and I'm going to put that percent there so just I remember, hey, remember this is a percent relative uncertainty. So I need to do the same thing with error 2. Okay, so my percent for error 2 is going to be the error over the magnitude of the measurement, which is 58.679, and again I need to, I missed my equals, multiply by 100%. Okay, so then my percent error 2, when I did that calculation, I get 0.0017. Okay, so again, I'm just dealing with term A right now. I will deal with term B in just a second. So now what I can do is I can actually divide my 3.27 divided by 58.679, get that number and then propagate my error. All right, so if I'm going to propagate this again, I've got my percent relative uncertainty. So we're going to call this percent error for term A. Again, I'm just trying to keep track of where everything is. So this is my square root, and I'm going to sum the squares of my percent relative uncertainties, which just sounds really, really complex, but hopefully as you see how these problems are worked, it's not that complex, but it sounds really convoluted. Okay, so you can see I have squared each of my percent relative uncertainties, and I'm going to take the square root. So my percent relative uncertainty for term A is 0.92%. Okay. Again, we need to make sure we take this percent relative uncertainty and we need to turn it back into an absolute uncertainty. So now that we've propagated the error, we're going to turn it back around and turn it back into an absolute uncertainty. Okay, so my absolute uncertainty for term A is going to be my 0.92. I'm going to divide by 100, and then I'm going to multiply by my 3.27 divided by 58.679. So if you do that calculation, actually I should, maybe I'll just write it in green under here. So this number, just the plain old division part, is, I'm going to give a couple of decimal places, and then we will get this error in just a second. And then I'm going to multiply by the magnitude of my measurement. Again, and maybe I'll just pop back to my equations because it's easy to get lost in these. Oops, not this one, this one. So again, I'm going from percent relative uncertainty, so that's why I'm dividing by 100 instead of multiplying. And here I've got my relative uncertainty. I'm calculating my absolute uncertainty, hence the multiplication of the magnitude of the measurement. Again, I'm just doing everything in reverse there. Okay, let me get back to not this one, this calculation. All right, so the error associated with term A, let me find that number. Again, it's got quite a few zeros in front of it, is right there. Okay, so where I'm going to round is I'm going to round to 1, 2, 3, 4 decimal places. So 1, 2, 3, 4, which means I want to round to that 7. So I am actually just going to erase that 2. And so this is plus or minus 0.00051. Okay, so again, that is for our term A. Now I need to do term B. So in the end, this is going to be plus whatever I get for term B. And I'm wondering if I might need another page. But let's just keep trucking and see if I can fit it on one page. All right, so I'm going to do the same thing for term B that I did for term A. So let's get, I'll just put it right here. Let's get a percent error for term 3 here. And I'm just doing the same thing that I did for term A. So I'm going to take the error and I'm going to divide by the magnitude of the measurement and then multiply by 100%. Okay, so then my percent error for term 3, let me find that calculation. Here it is 0.24%. All right, the same thing for our last error, error 4. Actually, it's not really because we still have to do our addition. Same deal. I'm going to take my absolute error or my absolute uncertainty, divide by the magnitude of the measurement, multiply by 100%. And so the percent error in my term 4, here we go. 0.0099%. That decimal really did not turn out so great. Okay. Now that I have my percent relative uncertainties, I need to use them to propagate for my multiplication division. So again, my percent error for term B, I'm going to have my big square root And I am just squaring each of these errors. Oops, percent, don't forget the percent because it's easy to do that, and then it's easy to lose track about if you're dealing with percent relative uncertainty or absolute uncertainty. I have done that. You do all this work and you realize that your numbers are wrong. It's very frustrating. Okay, so that is squared. I'm going to add them together and then take the square root. So my percent error in term B, hold on, let me find that calculation. Here it is. 0.24%. All right, so that's great. That is our error in term B, but now we have to take that percent relative uncertainty and turn it into an absolute uncertainty. And before I do that, let me go ahead and just get a number for this. 8.35 divided by 40.215. And again, I'm just going to put in multiple decimal places, and we'll go plus or minus whatever we get here. Okay, so to convert my percent uncertainty into my absolute uncertainty, and this is uncertainty for B, I'm going to take my percentage and divide by 100. And then I'm going to multiply by the magnitude of my measurement, 2076. And then that will give me my error, which is 1, 2, 3. It's actually really close to the error from term A. Okay. All right, so let's write that error in 0.12350. So I need to round to the fourth decimal place. 1, 2, 3, 4. So I'm actually already there. That's great. That makes it. I'm not finished yet. It feels like I should be finished, but I'm not finished yet. So all I've done is my 2 division problems. Now I have to do my addition subtraction problems. And actually, I really want to try and get this on one page. So I'm going to try to utilize this upper right-hand corner as much as I can. Now, the great thing about going back to addition is I'm just going to square my absolute uncertainties. I don't have to go to percent relative uncertainty, so it makes it a lot easier. All right, so let's first maybe get an actual number here. Okay, so actually adding these two, I'm just going to put in hopefully enough decimal places, and I'll go plus or minus whatever we get at this point. Okay, so we'll call this maybe I'll put it down here, error total for our final, or maybe error final would be better instead of error total. Again, you can call it whatever you want. So because it's addition subtraction, I am simply going to square each of my errors, sum them, and then take the square root. So again, I'm pulling my errors from here. It's really tempting to start pulling these errors again, but you've already dealt with them. You don't need them anymore. You want to make sure you use from that finalized first step. So I'm going to have my 0.1230051. Again, that needs to be squared, plus my second error. Bear with me as I try to kind of squish this in. That is a squared. And of course, everything is under the radical. So if I calculate my final error for this, and again, the great thing with addition subtraction is you get absolute error back out, so we don't have to convert from percent relative to absolute uncertainty. So the error for this is 0.00071. So I am just going to transfer that up here. Again, it's easy to drop or add a 0. So let's make sure that it's rounded to the right place. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is rounded to the correct number of sig figs. Again, I gave the extra digit here, but I gave it subscripted. So our final answer then for this calculation is 0.2633 plus or minus 0.00071. Again, you could also convert that to scientific notation, and that would be 1, 2, 3. That would be 7.1 times 10 to the fourth. If you convert to scientific notation, remember, just keep that one subscripted, because it's really important to make sure that you communicate to the reader that that 1 is actually your second digit in your uncertainty and not your first. Okay. Whew, that was a lot of calculations, and I'm glad that I was able to get it in on one page. So that is how you propagate your error. Now, these are obviously pretty simple calculations that I had us work on here, but you can imagine, if you think about the chemistry problems that you do and the labs that you're maybe doing in class, if you're actually going to propagate all that error, it does take quite a bit of time to do. But then in the end, you can say with certainty how many significant figures your answer should have. You can justify that, and you can know exactly what your error is and know if you have just a massive error, or if you have, like in this case, we have a really, really small error and we're able to do lots of sig figs. So I hope you found that helpful. Thank you for joining us for this live stream. If you have any requests for topics or problems, you can either leave a comment in YouTube, or of course you can comment in Facebook, or you can email me. All of those places I check regularly, so just please leave me a comment. Thanks so much. Bye.